After receiving bachelor's and master degree in engineering, he completed his PhD in development studies from IGIDR Bombay. Professor Kavi Kumar has been associated with various international and national institutions, including World Bank, International Institute for Applied Systems Analysis, Potsdam Institute for Climate Impact Research, GIZ, British High Commission, Tata Energy Research Institute, Institute of Economic Growth, etc., for various research assignments. During 2008 to 15, Professor Kavi Kumar had coordinated the activities of the Center of Excellence in Environmental Economics, supported by the Ministry of Environment, Forest and Climate Change, Government of India. He's widely published. He has published in several peer-reviewed international and national journals like Journal of Asia Pacific Economy, Climate Change Economics, Ecological Economics, Energy Policy, Global Environment Change, International Review of Environmental Strategies. Today, he'll be giving us an overview of climate risk and agriculture. He'll cover the state of research on how climate change could impact and has impacted agriculture. What are the methodological issues? What is the empirical evidence? He'll talk about climate risk, migration, farmer suicide, climate change implications for economic growth. He'll also talk about some potential research questions in this area. In today's age where risk for climate change has become very, very real, I'm sure this area is of interest to many participants here today. So I now request Professor Kavi Kumar to deliver his talk. Sir, please.
Thank you, Dr. Tirtha. Good afternoon, everybody. Let me first share my screen. Okay, hope the screen is visible to everybody. So thank you, Dr. Tirtha, again for that kind introduction. I'll be looking at little esoteric topic, hopefully, probably for some of you. This is on the climate risk. So little futuristic, but it also is contemporary in my view, because a lot of things that we are discussing are based on what we are currently seeing. But of course, the future is also implicit in the discussions that we are looking at here. So climate change may be a little, on and off coming, but I will set the context with the climate change. But bulk of the discussion in terms of the models or the empirical exercises that I discuss largely emanate from the current climate variability and weather variability related issues. So with that background, let me just put the structure over there for us to look at. I will be trying to provide a policy context for why we need to be looking at climate risk or climate change risk, so to say, and then provide some discussion on particularly on impacts related to agriculture sector, on methodological aspect, distributional issues, and going beyond the standard empirics like yield impacts and so on. So I'll also try and provide some context to the climate risk assessment that at the policy level people are trying to do, which is beyond the economic journals and the publications that we care about. A lot of work is otherwise also happening on trying to get a comprehensive picture of distributional aspect across districts and so on. We'll try and get some glimpse of that and try to provide some research questions that we may be further interested to look at. It's a fairly vast subject. I'll try to, Dr. Tirtha, how much time I have?
You can take an hour, 15 minutes, and then maybe 15 minutes question answer.
Sure. That sounds fine. So feel free to stop me in between if you need any clarification also. That's not an issue with me, or you can post it on the chat. This is online mode. We all know the problems. But I'm flexible to any mode that you're comfortable with. So what's the context? I hope some of you or most of you are familiar with the climate change problem as such. In case you are not familiar, just for the sake of completeness, let me put it simplistically. What it means is that we are dealing with, there is a difference between weather and climate, first of all. What we observe on a day-to-day basis is weather, temperature, precipitation, and so on, that you observe on a day-to-day basis or a short-term basis is called weather. When you look at the long-term changes in these same variables, we are referring to climate change. How is this happening? Largely because of the anthropogenic activities like greenhouse gas emissions emerging from the fossil fuel usage, which is largely involved with most of our economic activities, be it electricity generation or transportation or any such activity. So we basically have most of our activities very closely linked to the fossil fuel usage and the greenhouse gas emissions. These greenhouse gases essentially include gases such as carbon dioxide, methane, nitrous oxide, and some other trace gases. So these gases are naturally occurring gases, but it's just that their presence in the atmosphere is essential for our survival on the Earth. But the way in which we have added to think of the set of gases that I just mentioned as a blanket surrounding the Earth's surface or Earth's atmosphere. So we basically increase the thickness of that blanket through our activities in the last post-industrial revolution era. And the way in which we have increased is essentially making incoming radiation from the solar energy to penetrate through this blanket fairly easily, but outgoing radiation or outbound radiation from the heated Earth is actually getting trapped and sent back again. This is exactly the phenomena that you observe in greenhouses in the nurseries and so on. Same phenomena is happening at a very macro level. So that phenomena is leading to what we call as global warming, as in simply increase in temperature. But the Earth's system could respond in multiple ways once the temperature changes. Sum total of all that is what we are calling as climate change. So in nutshell, what we are worried about is that this, for instance, you think of Trivandrum, the temperatures that expected in month of May to be a certain number on an average. And that average number is likely to increase in the medium to long run. So by what amount it is going to increase, those are all the predictions that we deal with regard to the climate change predictions. So we are looking at once that climate changes, what implications it will have for sectors such as agriculture because of the close dependence on the atmospheric parameters or variables. So that's the context. So basically, these climate change impact assessments have been a focus of bulk of climate-related research from the early 90s. But they have been largely initial stages were at a academic level, but they become a little more operational or policy-oriented over time. They moved from direct to indirect in the sense that they used to be largely focused on yield impacts. Now it's just not yield. We wanted to know more than that. From aggregate to distributional issues, these are all the changes in which the climate change impact assessment work has been kind of transforming over time. Within all the sectors we are going to focus in this lecture on agriculture. Again, it's been one of the sectors that attracted a lot of attention because of its direct connection to the climate or weather. So the distributional issues have been at the center of most of these climate change problems, not just in the impact issues, but even on the, for instance, greenhouse gas mitigation or the reduction of the greenhouse gases is center of the climate change negotiations across the global nations. And that's a major thorny issue because historically some of the currently developed countries have emitted a large amount and the developing countries have correspondingly emitted much less. So there is always a kind of a tension in terms of who should bear the future emission reduction costs. These costs are not insignificant, so there is a major concern there in terms of even the impacts are not likely to be uniformly distributed. There are countries which are likely to be better off under the climate change conditions. Certain countries which are currently curtailed in terms of their growing period, for instance, all the higher latitude countries like Canada, Russia, and some of these countries could be better off under the climate change scenario. Of course, there is no, it's not just, as we said, climate change is not just a temperature change alone. It's a combination of temperature change, precipitation change, change in the frequency and intensity of some of the extreme events and so on. So, but at least from the broad perspective, it looks like some countries may be better off, some countries may be definitely worse off. India, of course, it's possibly going to be adversely affected. That is where we are actually interested in this talk. So there could be distribution differences or in terms of the cross-country differences exist both in the mitigation side of the greenhouse gases as well as the impact due to climate change. And it's also like within those countries, the poor may be more disproportionately affected than the not so poor. And these issues, which will also empirically establish as we move forward. Um, and there is also a concern about the impacts being nonlinear, because climate change, uh, most of the work generally assumes that uniformly or a gradually changing climate variables would be what are triggering the impacts. But it could be the case that you may have um, crossing, you may be crossing a certain threshold, and as a result, non-linear impacts could be also very much part of the discussion. Still, of course, as I said, the context, I must also confess that non-linear impacts are not very much part of the current state of research. Of course, they need to be brought on board as we move forward. Just to give you a glimpse of global differences, this is temperature impact of the temperature rise and per capita output. This is not one sector, but across all sectors, aggregated impact on output level at a grid level data. So as you could imagine, the northern latitude countries are relatively better off, the green indicating that they are not adversely affecting. Pink and red is basically indicating that the countries are going to be a little more adversely affected. Of course, these works constantly keep getting developed and further refined and so on. We are going to kind of zoom into one sector and focus on how the research gets done within that. But to set the stage, I'm providing the macro picture first. The same kind of a thing you can also look at the India level. So this is done by Mani et al. There's World Bank group in 2018. So they basically didn't focus on all these sectors per se, but they just assumed that increase in temperature and precipitation or change in precipitation would lead to change in the living standard. The living standards are being captured here through consumption expenditure changes. They used NSS data to capture that. So it's not looking at, let's say, temperature change influencing agriculture, from that what influence it would have on the living standard and so on, but directly trying to connect these two pieces. So they basically looked at a possible response function, any sectoral level response function or aggregate response function to be this kind of a concave function, which essentially shows that up to currently we are operating almost at the optimal level of what in terms of the sensitivity is concerned. Any further increase in temperature is likely to push us down that downward sloping concave part of the function. And that's where the concern is essentially emerging. So this is basically expected temperature rise coupled with this kind of a response function is what they would actually use to calculate the change in the consumption expenditures, and which are basically reported here in this graph in this map for different climate sensitive scenarios, essentially indicating that because to predict the future, you also need to make the projections on the temperature change, precipitation change and all, which actually need to be coming from climate models, which will be inputted or used as input into your calculations. So these two scenarios are milder climate change, and you can think of this as a milder on the left and a little more severe on the right, as well as the climate change predictions are concerned. So we're basically seeing the numbers per se are not so important in all throughout this discussion. It's just the trends and the kind of patterns that you are seeing that may be more relevant to take home as the message. So you could see that there is a possibility that some of the central parts of the country are more going to be more adversely affected than the rest of the country when it comes to this aggregate level impacts. So we're not looking at one sector, but as I repeat, across all sectors. This will set as a tone for why we should be looking at these impacts in a little more detail, and that's what precisely we're going to do. To also put in the, I mean, those of you who are familiar with the climate change economics would be knowing that there is this most important notion called social cost of carbon, which essentially means for each unit of or each ton of carbon being emitted, what is the social cost? So it essentially provides an important input into your mitigation policies as well as adaptation policies on climate change. So, for instance, if you want to kind of transform your transport fleet from conventional mode to electric fleet. So there is a cost associated with it, but what the benefits you could actually measure in terms of the obviously understandable local pollution benefits, but you can also measure in terms of avoided future carbon emissions and then associated avoided future climate change. For doing that quantification, you would be needing social cost of carbon. And that's how the connection to the policy emerges. But how do you arrive at the social cost of carbon is what I'm just providing you here as a just a illustrative graphic. So you basically have climate change projections, sector-specific climate response functions, like that concave response function that I showed in the previous slide. So they come together to assess, provide you sector-specific climate change impacts, which when translated into economy-wide aggregate impacts, coupled with the discount rate, will lead you to calculate your social cost of carbon. You can also actually measure the social cost of carbon at a country or across all countries and so on. But the point is, into this social cost of carbon, one of the crucial input that's going in is economy-wide impacts, into which the sector-specific impacts are going, and that is what we are going to focus on. Within this also, we are going to focus on this climate response functions. How do you actually measure these guys? That's going to be focus of our discussion. So I'm picking up, as I said, within that climate response functions, I'm looking at agriculture, and that the existing studies on climate change impacts on agriculture, which is essentially to calculate that response function or sensitivity of agriculture to climate change, could be visualized to various channels. It could be yield impacts or revenue impacts or impacts on the total factor productivity, and then of course also the interconnections between them. So all the green lines here indicate that we know reasonably well. The red is, of course, we know very less about it. The other color, I don't know what the speech color maybe, is not so well understood, but not as bad as the red. So that's the current status in a nutshell, but we'll go a little more detail into each of them. So as such, impact literature has been fairly old. I mean, as old as me. I started my own research in the field of climate change impacts. It was way back in early 90s. At that time, largely, it is a science-driven approach. But as I just showed through this symposium issue that came out in 2017 of REAP Journal, it's still a burning issue. The methodology has not yet been settled. We still are struggling to figure out what exactly is the right methodology to look at, partly because the changing goalpost. We simply don't want to know one number of what is the climate change impact, but our nature of questions are also changing. As a result, you have still an unresolved methodological debate there. There are broadly two main approaches: process-based models or statistical models. The statistical models further are subdivided into cross-sectional, panel, or long difference models. We'll be quickly looking through some of these features of some of these models. Process-based models were the first one to arrive on the picture. The one which I'm showing is from the 2017 symposium issue, but the similar approach is what has been first used by Cynthia Rosenzweig, Martin Parry way back in 1991, I think. This was a long history of these process-based models. Basically, they're looking at a combination of agricultural models, which are basically crop response models or crop simulation models, combined with economic models. So it's basically take a crop model like a wheat growth model or a rice growth model or any other particular crop model, and you kind of calibrate it to a given location and then perturb it with the future climate change projections to see how the yield changes, and feed that yield changes into an economic sector model or a general equilibrium model to assess the impacts at the welfare level as well as the aggregate economy-wide impacts. That's basically the logic of these process-based models. So which is also represented here through this simple graphic here. So you basically take a data on the geo-bio various aspects of the crop growth activities as well as the prevailing climate there, feed it into agronomic models, which is basically coming from the crop science specialists, and then assess the physical response of the crops in terms of the yield or any other changes, and then use that as a trigger into your economic models to calculate your welfare implications. In the contrast, the other approach, which is basically statistical model, uses a similar database, but just basically converts all that into a cross-sectional evidence or a panel evidence of farmers' response, basically using statistical tools to estimate such relationship. And so you basically no notion of measuring physical impacts. Directly you get your climate response function, use that to calculate your economic implications. So the process models are more interdisciplinary in nature, whereas the statistical models, any discipline can be using. Largely, they were preferred by economic disciplines and social science disciplines. Right? So that's basically the two broad approaches. I provided some of the references to that, but there are many more references related to these broad two methodologies. Yeah, I just give you a glimpse of this economic approach in the Indian context, coming from almost 2 decades back work. This is basically what you're basically doing is some kind of a farmer's profit maximization problem subject to usual production function, except that the production function is now involving some of these environmental variables also. So we are assuming some kind of a separable production function in this. These are the usual inputs, and then there are environmental inputs, or let's say temperature prevailing in a place, or the precipitation, and so on. These are not subscripted, as you can see, with respect to the farmer I. They are basically independent of the farmer itself. So we are assuming in this case that for the economic approach or the process-based models, some kind of a separability in the production function. So you estimate this F2 separately and then feed that along with the F1 into your economic model framework. So we tried to do that. This exercise that I'm just showing way back in mid-90s, we tried to do. Basically used epic crop model, which was one of the generic model, not specific to one crop, but multiple crops. So we use that crop epic model for calibrating rice and wheat across multiple locations in India as far as growth is concerned, and then assess the impact of the yield of these crops at these places following certain climate shocks. Those climate shocks came from these climate models prevailing at that time. These were, of course, now history. They don't even exist now, this kind of modeling forecasts, but they were at that time prevailing forecasts. So we basically use that to predict the yield changes and use those yield changes as shocks into an EGRIM model. EGRIM model was one of the widely used applied general equilibrium model developed by T.N. Srinivas and Kirit Parekh and others. So basically use that to calculate the dynamic impacts with price effects in the year 2060. So those impacts are essentially showed here. So the GDP loss, under different scenarios, how the GDP is likely to aggregate impacts like GDP decline, per capita calorie change, and also more importantly, distributional or welfare impacts in terms of the proportion of population in the bottom expenditure classes in the rural and urban areas. This is a more standard economic modeling work that you can think of for a climate change impact assessment. One of the things that is often criticized about agronomic or process-based models is that the adaptations that farmers can undertake are needed to be done one by one, because in the process, in the crop simulation models, suppose you change the planting date or the harvesting date, or you change the irrigation schedule. All these things the farmer can do routinely. Variety of such changes he or she can undertake routinely. But we basically have to incorporate those changes systematically one by one to see what impacts each of them would have on the yield changes and so on, which is very laborious. At the same time, you won't get a complete picture of the host of adaptation measures that a farmer can undertake. So that's one of the critical criticism against the economic approach. And as a result, if you don't account for that, you are overestimating the impacts because adaptation is not completely accounted. So in the other criticism is that there is with the climate change, you have higher carbon dioxide concentration in the atmosphere, which is actually the root cause for the climate change to start with. But carbon dioxide is also an aerial fertilizer for crops. So it facilitates faster photosynthesis. That's like a aerial fertilizer is what the term used in the literature. So that is not feasible to be incorporated into this modeling framework directly, but you can make adjustments to bring that on board into your calculations, because you can create artificial environments in which the crop model is calibrated, so that in that artificial environment you can have higher CO2 concentrations to see what way the crops respond, and use that to calculate your yield impact and so on. So this is typical. This kind of modeling framework is very much the way in which the agronomists use for the climate change impact assessments. On the other hand, the statistical models, which was largely propelled by this seminal work by Mendelssohn, Nordos, and Dingishaw in AER 1994, they called it as Ricardian Approach. Essentially, they used the logic of hedonic pricing method in environmental valuation that you are familiar with for your assessment of how a farmer in, let us say, sitting in Punjab would respond to the temperature conditions that would be prevailing for a farmer sitting in, let's say, Tamil Nadu. So overnight, if the temperature and precipitation conditions that the farmers in southern part of India were to be transferred to the same conditions to be experienced by farmers in, let's say, Punjab, Haryana area, what could be their way of response? That's essentially the underlying logic of these cross-sectional models. So they basically use some kind of a relationship like this. So you're looking at the original work by Mendelssohn and his colleagues was to use land prices, but in a country like India, where land transactions are relatively rare, you don't have very well documented land prices. So you may have to use a proxy for that. And many of the studies that we subsequently did, we were using either, let's say, net revenue at the farm level, or some kind of a, or even yield, for instance, to capture the gross revenue and so on. So it's some output is what we are looking at, some indication of output here, which is basically at a cross-section level. That means in a country like India, you can take the cross-section units to be like districts, or even smaller units than that, and the prevailing climates at those places, which is represented by this CI, and then a number of control variables, because whatever you can control through, because this is a cross-section regression, and you can have a lot of omitted variable biases, a lot of variables you may not be able to clearly capture, and to the extent possible, all that are included in this vector of Xi. So once you have that, the beta coefficient you arrived at will give you a idea about the climate sensitivity, or the climate responsiveness of the agriculture under consideration. So pictorially, this is what basically we are looking at. On x-axis, if I'm putting temperature, and some output on the y-axis. So each crop would have a, as we have seen in the previous slides, each crop has a kind of a concave response function. So the conventional agronomic or process-based models assume that the farmer is going to follow this path. As the temperature increases, any one crop that he or she is growing, you will follow exactly the way in which it is moving, with small modifications on the way in which the response function could be modified or tilted. But in reality, what could happen is that the farmer could switch in between. Whenever the conditions seem not conducive for the current crop, he or she could completely switch to a different crop or a different activity altogether. So you basically have the response functions are stitched together of different possible activities that the farmer can undertake. So we are interested in basically tracing this envelope of response functions. So which is what cross-section models try to capture for you. So as a result, if you have estimated beta correctly through this previous equation, you're able to capture this, the red line, accurately. And that's what is going to capture for you, or tell you correctly about the climate impacts with appropriate accounting of the adaptation. But of course, there are problems with it. As I already mentioned, a large number of studies have been undertaken using this logic. Mendelssohn Norda's original work was one of the highly cited work in this field. It was applied to 90 plus countries by 2016, and it continues to be a hot topic. A lot of people try to use it with a lot of limitations also. Some of the major problems are that you can be missing relevant control variables. You could be making assumptions about prices because there is no accounting of the price changes in this. You assume, we'll talk about price changes, how the statistical models miss out. In the agronomic model, we do capture the price impacts carefully, but here there is no relative prices are remaining constant is the underlying assumption that goes into this, which is a questionable one, especially when you are measuring the welfare impacts. And there, of course, there could be endogeneity issues like irrigation and so on. But major concern is omitted variable bias, because you may not be able to capture all relevant variables that could be leading to change in your output variable through your vector of control variables. So that led to emergence of panel models that came through Dutchness and Greenstone 2007 AER paper. So this was a modification of the cross-sectional models. So it's just that you now can use both time as well as the cross-section in this. So instead of climate, now you're actually using weather. Just to put again in perspective the data description, when you're using the cross-sectional models, for instance, if I have, let's say, 300 districts of India over which I'm doing the exercise, for each of the district, the temperature appears as the average temperature that that particular district experiences in any particular month that I'm choosing to include in my response function calculation. That the temperature that I use for that district is going to be emerging as an average over 30-year period. So it's like January temperature if I'm taking, it is an average over 30 years of the district's January temperature. That enters as the temperature in the cross-sectional models. In contrast, in the panel models, you basically take all those 30 years data as part of your temperature data. So the advantage is basically that you have more data to look at so that the variability can be better modeled. More importantly, you can account for all the cross-sectional unit specific differences through fixed effects. That will enable you to estimate your beta more accurately. So the basic idea is that the climate variability or climate change induced the changes in temperature that are coming through climate change are are already getting reflected in the existing data set. That's the underlying notion we are using both in the cross section as well as the panel models. In the panel, it is the variability that you see both in the time and space is being utilized for that future expected changes in the temperature and precipitation. That's the basic logic that we are using here too. So in terms of the pictorially representation, representing the same earlier graph, now because we are using every year's data, you're likely to be not capturing that envelope that we earlier showed, that red envelope, but you may be actually going along one of these paths. And as a result, when temperature changes from W2 to W prime, I may not actually capture the impact as moving from A to B, but rather moving from A to C, which essentially means I'm overestimating the impacts. That's a concern. While we are estimating the beta correctly or more accurately, your impact is not accounting for the adaptation as effectively as it should have. That's the concern. So you have on one side you are gaining, another side you're losing. So even in these models, there are concern about omitted variable bias and so on. But a large concern is about not accurate accounting of the adaptation. Because adaptation is not considered through one or the other channel, but it's a multitude of actions that the farmers can undertake. So that should be self-reflected to the data, the statistical process that you're using rather than through one-by-one incorporation as the process-based models try to do. Now, the one way to overcome this problem is through what we actually refer in the literature as long difference models. So the picture bottom of the slide here shows that you basically have a long data for, let's say, 1970 to 2010. I use the first 10-year average as one data point and the last 10-year average as another data point, and basically look at the difference between these two data, these two 10-year averages as my input into the calculations for this estimation of this equation. So I'm looking at the delta yi, which is basically difference between the average in 2000s versus average in 1970s. So why am I picking up these long distinct time periods? To capture for me the changing climatic conditions that could have prevailed. And the short-term changes are kind of subsumed into the average that I'm using. So as a result, I will be able to assess the beta more accurately with adaptations incorporated into it. That's the basic underlying logic here again. So some of the current works are trying to use this long difference approach to overcome the limitations that the cross-section models provide, give, as well as the adaptation concerns that you have understood in the context of panel models. So some work that we have done for India's level, we base at All India level, particularly with focus on rice. We have estimated that around 21% of the short-term impacts are reduced to long-term adjustment, which essentially means the panel data models are overestimating the impacts to the tune of about 21% than what the actual assessment should be. Again, I must confess here that most of the discussion that I'm going to make, we are basically dealing with an elephant and a blind man kind of scenario. We're trying to touch at one point and trying to say this is exactly the climate impact. Some other people touch it at another level and say that this is the climate impact and so on. So it's like we're all dealing with fairly unknown entity. So no work is complete. That's the basic premise on which we should be looking at this. A little understanding of adaptation is also worthwhile to think about. Because adaptation is a fairly complex thing here, because the economic agents respond in multiple ways that's very difficult to model. I'll give this example not through the agriculture, but through electricity consumption. That could be a lot more easier to understand. So, of course, as economists, we use these words intensive and extensive adaptation, but in the context of climate change, how these things matter. So think of a room where you are sitting and you have a usual cooling equipment for the room, like a ceiling fan. And when the temperatures are changing outside, like you are used to this current cooling equipment providing you the benefits that you are looking for. But when the things are changing outside, when the temperatures are regularly increasing, what your immediate reaction could be, you might actually use the same cooling equipment more intensively. You'll operate this fan more number of hours with higher speed and so on. When you realize that this level of adaptation is going to not really give you the desired outcome, given that outside temperatures are increasing more drastically, so you may have to invest into a little more a costlier adaptation strategy, like a air conditioner or something. So that's what the transition is going to be happening at the economic agents level at some point. So they might initially adjust with the, do the adjustments in an intensive manner of the existing equipment, existing cooling equipment, and so on, and then shift slowly towards an extensive adaptation, depending on how seriously they are considering the climate signal to be prevailing upon. So every agent has their own way of responding to that. So capturing that could be fairly difficult. And the cross-sectional models that we have looked at, they simply think that all possible adaptations are automatically undertaken by the economic agents. And that's not likely to be quite true, because there could be limitations for them. They don't have the know-how, they don't have the capacity, or either economic capacity or otherwise institutional capacity and so on. So those transitions, that the way in which a cross-section model assumes, is a very optimistic one. At the same time, not accounting for the possible adaptation strategies of this kind could also be pessimistic. So this diagram here basically is showing how the tracing of the changing climate would get captured by how the response function is modeled. If I have with adaptation, I have a one type of the slope for this response function. Without adaptation, I have a different type of slope for this response function. So if I don't estimate this correctly, my predictions of temperature and then translation of that into the yield changes would be grossly influenced or very significantly influenced. So the example that I told in the context of electricity consumption can also be converted into how farmers respond. So with adaptation, without adaptation could be short term plus the long term adaptations that the farmers can undertake. So this one is from the cross-sectional models. This is from a panel model. That's how you can visualize these two in terms of the response functions. So we are essentially estimating different animals in terms of the different ways in which the climate change impacts in both these modeling frameworks. Reality could be somewhere in between. We are still far from reaching there. In contrast, the adaptation in the climate agronomic models, this is coming from ICAR studies, Indian Council for Agriculture Research Studies. So they do a whole host of adaptation possibilities, technological adaptations, climate information service related, institutional or policy options that prevail. All these things one by one they incorporate into their process models and try and assess their implications in terms of the impacts. So by and large, when you sum them together, they're basically each one separately estimated and aggregated or added up. So you basically see that all these measures have fairly good implication or good impact in terms of reducing the adverse effects of climate change. Of course, that is expected, but it's not that all these things are going to be additive in some sense. They could be substituting each other or sometimes complementing, or sometimes could be not necessarily going together and so on. So this way of capturing adaptation could be a little problematic, but at the same time, economic models that we talked about, statistical models that we discussed, they also have their own limitation to capture the adaptation effectively. So the other dimension, what I described, all these more the cross-sectional panel models and long difference models, they're largely used in the context of either yields or revenues or combinations of them. So other studies that started looking relatively recently is on the TFP itself, the total factor productivity, how climate change is likely to affect that, and so on. One of our recent work we tried to, which I also shared with you to look at as a reading, we tried to use the NSS data for calculating TFP, and then used the kind of a Ricardian framework to measure the impact of temperature change on the TFP itself. So this is TFP in 2003 and 2013, 10-year gap. And first of all, there is a significant change between these two periods in terms of the TFP itself. That's something to be worried about. What is causing this change? Is it already, a part of this is being driven by climate factors, and part of it could be through other factors. And then given this TFP estimation, how temperature and rainfall influence the agriculture TFP. So as you can imagine, the temperature increases are likely to be adversely affecting, whereas rainfall changes or improvements, which are a part of the climate change. Under climate change, the general predictions are that temperatures are going to be increasing. Rainfall is also going to increase. But of course, there is a concern about whether the distribution of the trend, distributional parameters like standard deviation and coefficient of variation of that rainfall, they're going to be as desired or different than what we are hoping to witness. But nevertheless, mean is going to increase is generally the prediction. So there is a positive relation as far as the TFP is concerned for the rainfall, and negative relation with respect to temperature. This is not unexpected, but the implication of that in terms of the distributional implications is what we are looking at, distribution in a geographical sense. There are two types of distributional issues that one can talk about. We can look at the economy-wide, across different stakeholders, or across different deciles or expenditure groups. You can look at the distributional issues, and also you can look at geographical distributions to talk about. So we are here talking about the geographical distributions, and the left one is basically using the 2003 TFP calculations for the implications of climate change impact. For a particular future projection of climate change, I'm using the climate projections corresponding to RCP 4.5. This is a very benign climate projection. RCP 4.5 is very unlikely to be RCP representing RCP refers to representative concentration pathway, which basically talks about how the future is going to unfold, because that depends on how what our assumptions on population are, what our assumptions on economic growth are, and so on. All this translates into greenhouse gas emissions, and as a result, the climate change. So that's how the future is predicted in this RCP jargon. We use 4.5, which is a very mild future climate change, which is quite unlikely, but that's what one of the future projections that Government of India prefers to use for many of the calculations. So with that, if we use the 2003 TFP values, we get a one type of distribution which gets even more adversely distributed if you use 2013 TFP values. So essentially, we showed in the previous map that between these 10 years, over these 10 years, there has been a decline in the TFP that is getting reflected in your sensitivity also, and also reflecting in the distribution aspects. These are, of course, in terms of the rough numbers. We basically show that 1 degree centigrade rise reduces the agriculture TFP by roughly 4.5%. That's a fairly big impact. Translation of all that into GDP level and all, we are not attempting here, but you can do first order effects as well as the second order effects of that. I'll show that through another paper, right? This is a paper by Ishita Gupta and her colleagues in 2021. Basically, if you look at, for instance, a 5.7% increase in crop yields in 2009, so they used the period of 2018 to 2009. Over that period, if there were no change in climate, crop yields would have been, not one crop, but multiple crops put together, yields would have been something like 5.7% higher. But because there were some changes in the temperature and precipitation, crop yields were lower by the 5.7%. So essentially, it's a counterfactual kind. If this 5.7 were not to be there, what could have been the impact on aggregate GDP and so on? So that's how many of these, instead of doing a forecasting, you do a counterfactual assessment for impact assessments. So they do a first order effect of on the GDP using this kind of a 5.7% increase in crop yields, had the temperature and precipitation remained without any changes over the period 80 to 2009, and they are taking a 15% share of agriculture in GDP. The first order effects would be simply this multiplication of these two will give us a very small impact of around 0.8%. You would have had, if there were no drop in yields, you would have had 0.8% higher GDP, which of course at a consumption expenditure level, little more, like 2.8%, you will be observing. So this is what we call as a first order effects. Most of the work is essentially getting stuck at that level. But there could be price changes following the supply shocks. So there are global level studies which actually argue that because of some regions gaining, some regions not gaining, or having reduction in the production, there would be net effect not so significant. As a result, in a full trade model at a global level, aggregate welfare loss is approximated well by the first order impacts. That's a general conclusion we have at the so that's why prices are usually ignored in the calculations. But Ishita Gupta and her colleagues' work basically tries to capture this the price effects in a general equilibrium framework for India. So they use this kind of from the existing literature, the estimated crop yield changes in a counterfactual level to assess what implications it would have for different groups of economic agents. So the welfare loss to landless poor, they estimate to be 5 times more than the first order GDP effects. So that means there's a huge distributional differences. People who are poorer are going to be more adversely affected than the not so poor. That's not a shaking result, but it's important to establish it in a rigorous manner as they have done in this work. But they also show that with trade, the losses to poor are lower than without trade. This is in a closed economy. What I just said in this earlier point is in a closed economy. But if you bring in trade, the losses to poor are lower as expected. And more importantly, the distribution is a lot more uniform. And that means the impacts are going to be more uniformly spread across rich and poor and so on. So that's a very few studies actually got into this kind of a price effects, largely because of this general result that we are familiar in the agricultural impact studies. But process models, the agronomic economic models that I showed in the very beginning, still routinely go into the assessment through general equilibrium effects. But the statistical models that we talked about in between, they actually skip this entire, they stop at the first order effects and don't get into the price effects. That's where we currently stand with regard to the yield, revenues, TFP, and so on. But there are other studies which are also going beyond the yield impacts. One of the often talked about thing was this migration, people moving away from agriculture or rural to non-agriculture or urban areas. So there was a influential work by Feng and his colleagues in PNAS 2010, I think. So that actually looked at Mexico US border, how agriculture induced yield losses will lead to cross-country migration. And that is a very politically sensitive issue that led to a series of studies. So we did work in Indian context in this, trying to understand how the climate-induced agricultural distress or climate change-induced agricultural distress will lead to migration and so on. What we basically observe is that first of all, India's migration rates are relatively low compared to other developing countries because we have a variety of other reasons why we don't migrate as much as we should be migrating. Kaivan Munshi had a 2016 article in AER where he argues that rural networks actually act as an important deterrent for social networks, act as important deterrent for people to permanently move away from rural areas to urban areas and so on. So first of all, we are seeing fairly low levels of migration. But on top of it, agriculture distress caused by climate factors. So we do this in a two-stage modeling framework. We first estimate the impact of the climate change on agricultural yields and use that to see how use that as a trigger in the migration equation. So we see a very low elasticity compared to the developed country studies, that is Feng et al.'s work in 2010, that is between Mexico and US study. So we also expect that in future this elasticity could be increasing because we may expect more migration than what we historically observed. So that with that probably there could be higher migration rates and as a result a larger impact than what we are currently predicting. Remember all that in all these studies we use the existing data. So existing data is obviously limited by what variability it has observed. So that's one type of studies people have looked at. The other is another fairly controversial topic was farmer suicide. This was done by Carleton and again 2017 PNAS Proceedings of National Academy of Sciences, which attracted a lot of media attention again. So they basically, she estimated that over the last 30 years, warming in India has caused close to almost 60,000 additional suicides, a large majority coming from the farming community. So that obviously was refuted by a large number of authors. But simply methodologically, how did they go about and all? We wanted to recheck that. We again applied a two-stage approach for that, and also used more accurate, relatively accurate data. Of course, we have a lot of problem with the data collection process itself. So our estimates operating via the agricultural channel, 1 degree rise in temperature results leads to 4.8% higher farmer suicides, operating via 3.6% decline in agriculture productivity. So at least the channel was clearly established in our work, but we didn't get into the numbers to really translate this into how many more additional farmer suicide could be attributable to. But because there are many other factors, as we all know, that lead to the unfortunate reality of this farmer suicides, which could include debt-related issues, which are very difficult to capture in a large-scale modeling exercise like this. We also find, very importantly, a significant role played by the contagion factors. So past performance or past numbers dictate present numbers and so on. That's a very troubling thing, but you don't have much way to control that also in terms of the policy response. So that these are other directions in which the climate change impact in agriculture have progressed. These are not the only directions, but I'm just giving some glimpse of other directions in which climate change impact in the agriculture research has progressed. Other than this, of course, some of the climate extremes like drought have attracted a lot of attention. This is nothing to do with the exclusively future climate change. We already know that drought is a major issue as far as agriculture is concerned. And then under the climate change, one of the way in which these climate extremes are being predicted is that their intensity and frequency could increase. So if we know well about drought agriculture linkages now, we'll be in a better position to predict what is in store for us under climate change. So it's a completely different direction, but a lot of work has gone into this. Basically, other than the direct impact work on yields and so on, there have been indirect effects also, which are more interesting in some sense, from an economic literature perspective. Some actually looked at impact on wages. Some have looked at conflicts. Some have looked at performances like the wage rates, how the test scores increase, and based on which how the earning capacities increase and so on. These are interesting other dimensions of the drought, one of the highly studied field, which I don't venture to get into for this limited talk right now. But these are the other dimensions. I go back to the looking at the direct impacts on yield per se. So we're using some of the fairly recent data to relook at regional as well as aggregate level relationship between rice yield deviations and drought index. And drought index is here being calculated using both temperature deviation as well as precipitation deviation. So it's like lower rainfall, higher temperature. Combination of that is what is being captured here through the drought index. So basically, we look at that most of the regions are differentially getting affected, all adverse, but differentially also getting affected. So that translates into to look at whether irrigation helps us or not, and so on. So some of the conclusions that are emerging is that irrigation does help, but the severe droughts are not necessarily well protected through the irrigation alone. So you need other interventions to take care of those drought impacts. There is a important we need to be all aware at this point to remind ourselves there is a gap between the way in which the technology gets developed in the agriculture research level and then translates into field level. This work by Palaniswamy, EPW 2015, they document that only 22% of all the farm, the research water management related research translates into farm level implementation. So a lot of work remains unimplemented or unused. So that's something to be worried about. There is also a kind of work which tries to look at how crop diversity helps to overcome the impacts caused by drought. So there was a work by Afhammer and Carleton on India, which basically they painted a fairly rosy picture saying that diversity is helping us to overcome the drought conditions. But we relooked at that in a more detailed way. Our observation is that it did help us during the Green Revolution period, but post-Green Revolution period, diversity, the limited way in which it is being defined in a crop diversity, not the agricultural diversity. So the diversity in terms of the crops that you're using, that's not necessarily helping us too much in terms of overcoming the adverse effects of drought. So we need to bring in agricultural diversity. If that is the case, of course, it makes sense to say that drought effects are overcome through agricultural diversity. Of course, irrigation is one of the highly studied field. I'm not getting too much into detail there, but just to bring in this work by Zaveri and Lobel 2019, which actually looked at the wheat particularly and documented well that this green line here is basically the irrigation-induced benefits in the yields of wheat. So this is improved quite dramatically up to 2000, and then subsequent improvement have been very, marginal. The gray line here is basically the trends or the adverse effects caused by the changing weather conditions, which can also be climate change kind of thing. So this sum total of these two is essentially this blue line. This green plus gray is what this blue is. So essentially what we are seeing is that we used to have fairly large gains through the irrigation, but those gains are obviously coming down, especially in the context of changing climatic conditions in future. Dependence on irrigation alone is not going to fetch us a lot of mileage. That's a message that we need to be adhering to. I think I'll spend a little bit of time on just connecting the all this to a little more policy level work on the risk part, because that's I've chosen as my title of the talk here. So climate risk, those of you familiar with the Intergovernmental Panel on Climate Change, IPCC, would recall that there is this important notion called vulnerability that was brought up to assessment reports 3 and 4. AR4 represents assessment report 4 and AR5 assessment report 5. IPCC is this intergovernmental panel of climate and related scientists or researchers who bring out periodically every 5 years these assessment reports, which essentially are synthesis of the existing literature. These are very highly influential documents, influential pieces of literature that most of the people working in climate change take very seriously. So up to AR4, the notion was largely, because all these impacts that we started talking from the beginning of this lecture are so widespread, and we have focused on one sector, and that too we are looking at that sector in multiple ways. So capturing the impacts in toto is always difficult. So the IPCC tried to kind of assign a new notion called vulnerability and said, let's try and capture this vulnerability, which is a combination of exposure, sensitivity, and adaptive capacity of an entity. Entity could be a geographical unit or an economic agent or anything. So they basically said the impact is one part of this whole exercise. Eventually, we will be interested in knowing the vulnerability of a particular entity to climate change. So how much exposed that particular entity is to the climate variables and the changes in them, and how sensitive they are, and how capable they are in terms of adjusting. If you put them all together, you get the entities vulnerable. This notion has changed in AR5 because by that time the literature has moved forward and they said, let's not look at the end goal as vulnerability, but end goal as risk. So for that, basically, they looked at the hazard, which is a historic observation of the prevailing temperature and rainfall conditions and the future expectations of them. The sensitivity and vulnerability put together along with adaptive capacity as additional component, all these three things together formulate your risk. So an entity's risk is then assessed as against entity's vulnerability. In some sense, it's not a major difference, but the conceptualization for the policy level, it's relevant, but for our discussion, it is not so relevant. I would take them almost interchangeably for our discussion at this moment. So there has been a work by NICRA, that is National Initiative on Climate Resilient Agriculture. This is a policy level work by Ministry of Agriculture that basically tried to assess the, as far as the agriculture is concerned in India, how vulnerable it is and what kind of risk it faces under climate change. These two questions they tried to ask, and essentially they wanted to do that at a district level assessment. So obviously, for the either to vulnerability or risk to be measured, you need to capture all these things that I have listed above. So to capture them, you don't have an obvious measurements. So you go through what we generally do in the context of, let's say, HDI, an indicator-based approach. So you kind of put together apples and oranges through various indicators, add them up through usual normalization process and aggregation with a weighted aggregation and so on. So that's what has led to this kind of the assessment of risk due to climate change in agriculture in India as of 2020 to 2050. So the similar period, the vulnerability is shown on the right-hand side map. So the point I'm trying to show is that, remember one of the hotspot map that I showed in the beginning of the lecture, where it was not just agriculture, all sectors put together, consumption expenditure related hotspots. But if you are looking only at agriculture, this is the kind of a hotspot we are arriving at. So you have a differential hotspot across the two types of assessments. If you look at the aggregate impact across all sectors versus agriculture alone. Again, the distribution is not something I want to drive home as the message, but it's a way of doing this. That's what I want to drive as the message from this representation. So finally, a few quick potential questions that we can be looking at. A lot of research is still possible and still is needed in this field. What we just, I presented a lot of work from various authors, and it's one of the fast-moving areas as such, but still a lot more gaps exist. Some of them, to my mind, what come, I just share with you here. One is that this climate change, yield, revenue, productivity linkages that we tried to show in the beginning of the lecture through this triangulation, need to relook at them with more granular data. We are doing it a very aggregate. District is not necessarily capturing all the details the way we want. So it's a little more granular data. I'll come to the data related issues towards the end, but that's if you can manage to do with the more granular data, you'll get a better assessment. The other issue, most troubling issue, is that are the impacts based on the observed changes in weather and climate, because that is what is actually going into your response functions, and that's what we are using to making the future predictions, right? So are the impacts based on the observed changes in weather, climate, are they providing reasonable predictions of the future impacts due to climate change? That's a troubling and bothering question, because we can actually be doing a short-term planning with the current impact assessments. Particularly the estimated impacts on yields and some of the agricultural yields and all are not really significant compared to the large-scale gains that we are able to get from technological improvements. So that means climate change impacts are not so kind of significantly bothering us, that they can be overcome through technological changes. But probably we are missing something in this kind of an interpretation. We need different methods probably to capture the future impact estimations than what we are currently doing with the historic data-based climate response functions and using that to make the predictions about future impacts. Especially if you think that there is non-linearity in the system, then this is not making any sense. Of course, I'm cutting the very branch on which I'm standing. Most of my work I presented is based on this past historic data and trying to take it to future impacts. But we must be, kind of at least be honest to know that this is not necessarily what the future impacts probably are going to look like. They may be looking differently than what we're anticipating them to be. This, of course, in a policy context has a lot of role to play, because in the climate change negotiations at the global level, there are three angles through which the negotiations take place: on the greenhouse gas mitigations, climate change adaptation, and then the third dimension that many of the small island countries and other LDCs have brought forward is the loss and damage discussion. Basically, their argument is that we don't need to wait till some 2060 or 2070 when climate is going to actually change and so on. We don't even know whether that is the date by which the changes are going to happen, or they're already happening. So we don't have that clarity already. So there is a lot of impact already being felt by some of the small countries, and that's what takes them to feel that they're concerned about the losses and damages that are currently facing. So that to connect to that, you need a different future impact predictions than we currently are using. And of course, we also need to be looking at a little more detailed agriculture groundwater nexus. We have very little work on this field. We need a lot more, in the climate change context. On its own, probably there is work, but in the climate change context, how the groundwater gets changed and how that has implication on agriculture needs to be understood more accurately. Other important dimension is there is one of the labor productivity changes. That's an important dimension which we are underestimating. There's a recent work by Somanathan and his colleagues in Journal of Political Economy, where they look at heat stress due to higher temperatures would have definite impact on the labor productivity, um, especially in the labor-intensive sectors. So these, they looked at the standard industries like garment factories and other things, where you can actually intervene to create cooling. You can put in cooling equipment to facilitate labor productivity losses to be overcome. But we may not be able to do that in activities such as construction and agriculture. So there is going to be obvious impact on the output operating via the labor productivity. None of the works that I have discussed in the previous slides did talk about that kind of a dimension. Those studies don't look at what is the implication of climate change on the labor productivity and as a result on the agricultural output and so on. So that's a very important dimension to look at, because a lot of people are going to be working in more harsher conditions, and that's going to lead to a significant drop in their outcomes. Quality of output is also an important one. Very little work has been done on that, particularly horticulture related, commercial agriculture related issues, and fruits and vegetables. This is a major issue. We don't have much understanding on this. But last point I want to make is that while we talk all these things and we claim that climate change is an important research area and so on, both from the Prime Minister's office level, Niti Aayog and other important policy bodies, data is extremely difficult even as we talk today to access. I talk based on my 20 plus years of experience in this field. I struggled a lot to even get simple data like temperature data. We don't have, let's say, if you want to construct a response function, I very comfortably was saying that you will use district level temperature data and all. Where do you get that? We don't have an official document where that district level temperature data is published. So obviously temperature is measured by Indian Meteorological Department and other agencies at a meteorological station. Translating that to district level data requires a lot of understanding of GIS, and some of the disciplines are very comfortably able to do that, but social sciences, I'm not convinced that they're able to do it so easily. So everybody reinvents the wheel. It's an unnecessary exercise. For instance, in US, you have a county level handbook, just like your statistical handbook in India. You have a county level handbook, which is equivalent to a district level. You get all the required details, including soil characteristics and the climate and weather data in the handbook itself. You don't. So as a result, we have, let's say, I did some work and you do some work using your own construction of the data set, and we may be differing in our models as well as the data itself. So where is the difference emerging between us is not quite clear. So to overcome that, at least we need to ensure that there is a uniformity in the data that is being used, so that that's what you try to do as you progress. I mean, I remember the days when NSS data was not very easy to access. Now it became accessible. So things like that need to happen even in the field of climate change. Otherwise, it's becoming a little difficult. Everybody is operating with their own data sets. They don't share it with others. Um, so it's a little messy there right now. So for instance, as I say that for temperature and other climate variables, but at the same time, other important agriculturally relevant variables like soil quality, soil texture, all these things, there is no uniform place where you can get this in accessible form. That's where a big challenge lies. Of course, this is not peculiar to the climate change field alone, applicable to all other fields as well. But I reiterate, given that I have an opportunity to say so. So I'll stop there. Thank you very much for your patience. I'll be happy to take any questions that you have.
Thank you so much, Professor Kumar. Any questions? It was a lot of, you've actually given a very concise literature review, come empirical evidence, what exists in the field of climate change, risk, and agriculture. Anybody, any question? Okay, so because this is for students, so I would, on behalf of the students, I would maybe, because many of them are working on climate change and risk in agriculture, etc. So as you correctly said, that there is a big problem about data, regarding data, uh, data availability. And so even say, for example, when we look at IMD website, it's only the last month or last few days data which is available at a high frequency. So what would be the place where students, how do they get data for their research? If you could give them some suggestions on that. Climate, weather, temperature, etc.
Yeah, I think right now at least things are a lot better. You can actually get it from IMD. If you're comfortable to actually use GIS, then you can get 0.5 by 0.5 resolution data. That's weather data. You get, that means at that resolution, at each of the grid point, you get temperature, precipitation, and some other variables. Within temperature, you will get max, min, and so on. But then you need to be translating, because all other economic variables are at a different district level or taluk level or whatever. So you need to translate that. So that requires you to do the surface interpolation. So you can do that if you're familiar, but there is an ICRISAT is another place where you can actually access. They have done this surface interpolation already and have kept, but we don't know exactly, because to do the surface interpolation also you must make assumptions. So whether you are comfortable with their assumptions or not is the question. So you have to at least believe that's what I was saying earlier, that ICRISAT is not a government body. If this is done by a centralized agency like IMD itself does, through some subcontracting to somebody probably, and say that anybody who wants to use with the caveats can use this now. So that would be more appropriate than XYZ doing or I doing it myself. And so ICRISAT is one place, definitely you get. There is also in the India Water Portal, you get a lot of old data. I mean, unfortunately, you get actually a lot more data from abroad about India than in India. That's a sad part, but that's how.
So some options with students, because IMD data they have to pay, they have to subscribe for it.
The grid level data is for research organizations very nominally priced, not very high.
Okay.
Not very high. You can get it reasonable price. This is not like satellite data, which are very costly. This is Of course, there is I mean, you can also download it from various other servers, but you need to know the nitty-gritties of doing that. But even after downloading, translating it into readable format and all requires a little bit of coding. So it's not straightforward, unfortunately.
Yeah.
But you can do that. All that is doable.
Yes.
But I mean, the other data, like I was telling about the soil, for instance, many of these also required to control for the soil quality because districts might differ in terms of the soil texture, quality, and so on. That's even worse, actually. There is a National Bureau of Land Use Planning and Soil Survey situated in Nagpur. They're sitting with tons of data, and nothing is in the public domain. So most of them are in a non-digitized physical maps. So they must be having that. Obviously, to produce those maps, they must be having it, right?
The data.
I mean, I take every opportunity to bombard wherever, whichever committee I manage to sit in, I say that please share. Because this is not for you. You collected it for the sake of the country, right?
Yep. What you saying just before you, Professor Farzana Afridi, she was speaking on a paper. She was talking about this soil quality data, which they personally got digitized. She was saying that was the main work to convert it to digitize the data. But of course, they would be sitting with a lot of such useful information.
Right. No, it's just that in a user-friendly form is what we needed to make this data accessible, so that you don't spend time on that. You will spend time on something else, actually.
Correct.
Modeling strategy, because your expertise is in the modeling strategy. As an economist or a social scientist, your expertise is something else. You actually waste your time on the other stuff.
On that, yeah. We have one question. Ansi has raised her hand. Ansi, would you like to ask questions?
Yes, ma'am. Hi, sir.
Yeah.
Good evening, sir.
Good evening.
So thank you for this beautiful session, sir. So you were talking about the climate change and also talked about the irrigation facility. So when I conducted a study last year, like using secondary data from RBI bulletin reports, so it shows that irrigation per hectare. I studied the relationship between the paddy cultivation and the factors affected like hybrid seeds and irrigation per hectare, how it affected. But the study I run through Stata software and it shows that hybrid variety seeds and fertilizer all have important role and positive relationship with the productivity. But when I done the work, the irrigation per hectare, that irrigation is showing a negative relationship and many of the factors, and I conducted the data from 1992 to 1996. So I didn't get like why there is a negative relationship in the irrigation. Is there any factor which is explained through this climate change or something?
So this is done for a what area? Which geographical area?
I done the cross-sectional data of the all the state, like
All
India.
the states at a
All
state
the
level,
states.
state level
Yes,
data
sir.
you used.
Yes, sir. Yes, sir.
I think
All the
first of
states.
all, you have a very short period. You're looking at 92 to 96, if I'm not mistaken. That's what you said, right?
Yes, sir.
Yeah,
1992 to 1998.
98, fairly small period you're covering.
But during that period, I only show some like in Bihar and Assam, some flood is came. So that period, but I don't know how these affected the whole state. Like there shows a more importantly negative relationship.
Yeah, it also
And
depends on
even the
how.
paddy cultivation is more depend upon irrigation. So I got confused. Like the reality is different, and study is showing the other results. So I couldn't explain what is going.
No, I think first of all, we are, as in between I was saying, we are trying to, I mean, this is not relate directly, you didn't try to relate to the climate issues in this. But of course, you could have also used, I mean, tried to explain the differences in the paddy output with the prevailing temperature and rainfall and so on. And then use the irrigation also to explain it. So we basically, all of us are doing different uh, aspects and not really capturing the full picture carefully. So first of all, my immediate reaction is that I don't know whether you have captured the irrigation correctly, first of all, whether your irrigation variable is measured correctly or not. maybe there is an issue with that. You need to look at that. And then very small time period that you have looked at, probably it doesn't capture enough variability, and it could be a spurious relation that you're capturing there. So maybe you need to
Controls
go
what
back.
you have in your model. Other controls, you control for fertilizer and
You have to
other.
look at that to understand why this is coming as negative. So I think that's where, like, building the model carefully is more important than actually, which also, of course, very crucially depends on the quality of the data that you're using and definitions that you're following.
So we have Parama Shivam asking, if I use field level data for impact of climate change on horticulture crops, which model may I use for horticulture crops?
So the field level data is essential. Statistical models are being used at the field level also. But remember that for the statistical models like cross-section model or something to work, you must have enough variability in your, because you are trying to assess the impact of the temperature on your outcome. So the temperature has to sufficiently vary in your data. At a field level, if you're looking at a village level, there is not going to be any change in the temperature within that village. You need to pick up a fairly big area over which there is sufficient variability in temperature and rainfall. Then you can use any of the statistical models. Of course, you're going to be collecting the data, so you will be ending up using only cross-sectional data. Because over time, you won't be collecting, you will be at a snapshot collecting it. But you have to make sure that there is enough variability in your temperature, which is not likely to be happening if you confine your field of research to a village or a couple of villages and so on. I hope I'm making sense to you.
In the meantime, Himanshu has a question. He's raised his hand, Himanshu.
Thank you. Thank you, sir, for such an interesting and
Himanshu, your voice is breaking.
intensive.
Your voice is breaking.
Do you want to type it maybe?
Himanshu, would you type on the chat box? Your voice is breaking.
As you mentioned. Oh, one second.
Yeah, please type on the chat box.
I'm just writing there.
Yeah.
Mr. Parameshivam, I hope I answered your question.
Yes, sir. Yes, sir.
Yeah.
I got it, sir. Thank you.
Thank you. This is difficulty of the online mode. It's like you don't know whether you're actually convinced the other person or not.
Yeah. Very true.
Both sides
No,
of the difficulty.
Himanshu, have you typed? No, you've not sent it. The question is sent in. Yeah. Send something.
What are we going to measure the climate change? Oh yeah, that's a good question. Actually, see, the thing is, what you're measuring is actually weather. In the panel model, you're using weather actually, not the climate. Because for all the units of analysis, you're using annual information. Right? Because other variables are varying annually, so you're essentially also using temperature also annually. So typically, if you can actually put together a 30-year period data, that would capture for you sufficient variability in the weather to reflect the underlying climate. So 30-year is what I would consider as a reasonable. Anything more than that would be even better. 30-year period is what would be quite ideal. Again, the climate science uses the kind of a thumb rule that climate of a particular place is 30-year average of weather. There is nothing holy about this 30 year. It's a fairly long term is what they want to mean. But it's something that has stuck in the literature and all the work. That 30 year is a norm that we all mostly follow. From that norm, I would say that a panel data over 30 year would give you a reasonable picture. Okay.
I think we should, there's another lecture at 6 o'clock.
Oh, okay.
So yeah. So I think if I'll ask once more. If you have any more questions, please you can ask him now. Otherwise, we can.
You can also reach out to me. I'm more than happy to respond if you can.
That
I
would
have
be
left
that.
my. I'll be sending you the PPT, which you can circulate with the participants. At the
That
end
would
of
be.
it, you have my email address. You are welcome to write to me.
Sure. That would be very nice. So thank you once again, Professor Kavi Kumar. It was very helpful. I'm sure students would have learned a lot because, and with so many changes, so many studies coming up, this clarity was required. That what method, how does one deal with the question, what approach one should take, what are the limitations of the approach. So this is something which was very required. So thank you once again, and we are very grateful that you accepted our invitation and delivered the lecture today. Thank you.
It's my pleasure. Thank you very much. Have a great day. Bye.
Sure, thank you. And students, now this is for you. So our next session is at 6 o'clock. So we have Dr. Richa Kumar with us. So we'll meet at 6 then.